Earlier, we have looked at Newton's first law of motion. Now, we will jump to third law of motion. We will save second law for the last. A boy is trying to push a sumo wrestler. Who is exerting a bigger force? The boy or the man? Most of us will think that the sumo wrestler will be exerting a bigger force. Some of us will think that the boy, because he's the one pushing the sumo wrestler. But as a physics student, we should all know that the force is the same. They exert the same force on each other. Right? To help us understand this, we need to understand Newton's third law. And let's look at that now. Suppose a boy sits on the toilet seat and he exerts a force R downwards on the seat. Because he's resting on the seat, he's pushing the seat down. Of course, the seat did not move, but it does not mean that the boy did not exert a force on the seat. At the same time, the toilet seat supports the boy and prevent him from falling through by exerting an equal force R, a contact force, on the boy upwards. And this is the essence of third law. You have to memorize this. Newton's third law states that when body A exerts a force on body B exerts a force of the same type that is equal in magnitude and opposite in direction on body A. This is the learning outcome. You have to memorize Newton's third law. Now, let's look at third law in detail. Right, forces always exist in pair, action and reaction pair. And if we break down Newton's third law into its characteristic, there are three characteristics. Number one, the action-reaction forces always act on different bodies, which is why the third law states body A and body B. So there are two different bodies. In the case of the boy on the toilet seat, the force on toilet seat, so toilet seat is body A, and toilet seat also acts a force on boy. Boy is body B. So they are different bodies. Are the forces the same type? Yes, both of them are contact force. The forces must be equal in magnitude and opposite in direction, which can be seen that both R's are opposite in direction and they must be equal in magnitude for the boy to be stationary. Now, let's check your understanding with this question. Are the weight of the boy and the contact force on the boy by the toilet seat, are these two forces an action-reaction pair? To answer this question, let's look at the three characteristics. We ask ourselves whether they act on different bodies. Right, the weight acts on the boy, and the contact force by the toilet seat also acts on the boy. So it is the same body. So the answer is no. Both forces act on the boy, only one body. Are the forces of the same type? No, the weight is gravitational force and R is contact force. Are they equal in magnitude and opposite in direction? Yes, since the ball is stationary, the forces are balanced. Let's look at another example to understand this point better. We have a book, object X, resting in equilibrium on the body, object Y. You are supposed to draw labor forces to show these forces on X and on Y, and make it clear which forces are equal in magnitude and opposite in direction. Now, let's look at the forces acting on X. First, there is a force on the book by table X. The table supports the book so that it doesn't fall through the table. So there is a force, a contact force on the book by table. We call this Fx. But the book also has a weight. So a weight is actually the force by the earth. Now let's look at the table. Since the table supports a book, it pushes the book up. At the same time, the book is resting on the table, it also pushes on the table. So there is a force by the book on the table. Of course, a table has weight, so there is a force on the table by the earth. Don't forget that the table did not fall through the earth. That means it must be supported by the ground. So this is the contact force by the ground on the table. Okay, when you draw this diagram to answer the question, there are a few things you need to take note. First, if the force are balanced, you need to ensure they have the same length, showing that they have the same magnitude. You need to show that for the table, the total length of all the arrows upwards must be equal to the total length downwards. Right? You can see Fx and Fy are equal in magnitude and opposite in direction, and they form an action-reaction pair. They are acting on different body, one on X, one on Y. They are the same type of force. They are contact force. If you look at Wx and Fx, they are equal in magnitude and opposite in direction. But are they action-reaction pair? Yes, very good. By now, you should know that they are not action-reaction pair because they act on the same body and they are not the same type of force. One is a contact force, Wx is a gravitational force. Let's look at work example 2 on page 4. Suppose object X is a book that has fallen onto the table Y and has just landed on it. For the instant of arrival, that is when it just reaches the table, draw labor force diagram to show the forces on X and Y. Right? So do take note that once the book hit the table, it actually slow down very quickly and come to rest. What can we know about the upward force versus the downward force on the book? Now let's look at the forces on the book. There's a force on the book by the table that will be upwards, and there's a force on the book by the earth, that's the weight. Right, similarly, there's a force on the table by the book, Fy, and a force by earth on the table, Wy, as well as the forces on the legs of the table, that's by the ground, contact force. Okay, remember just now this book falls on the table and stop immediately. So Fx must be greater than Wx because the book experiences a net upward force at the instant when it just touches the table. It decelerates to rest very quickly or it bounces, so there must be a greater upward force. As for the table, the total upward force and total downward force should still be the same because the table is in equilibrium and the table did not move. However, Fy will increase because when the book hits on the table, this time round it hits harder than work example 1. So the force should be greater. If the force is greater now, Fy is greater, the ground must support it with a greater force so that it doesn't fall through the ground. So Ny also should be longer. right? So in this case, magnitude of Fx and Fy are bigger compared to their previous value in work example 1.